Physics 11th grade, Class 80 Solutions, Minerva Bilingual School. Here we go. All right, a charge we're calling Q1 has a charge of positive 7 microcoulombs at the origin. Okay, now let's draw that right now. We're going to say this point, this blue point right here, is Q1. So Q1, it's at the origin. We're going to assume that the coordinate plane has the origin right there. Okay. And another charge we're calling Q2 with a charge of negative 5 microcoulombs on the x-axis is on the x-axis at 0.3 meters from the origin. So let's call each box here, we're gonna go like this. I'm gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so there's Q2, and we're gonna call this distance 9 squares. We're gonna call 0.3 meters. Okay. Now, it says find the electric field strength at point P, which is 0.4 meters from the origin. So now I think that I actually should have just left this line here. That would have been easier. 0.3 meters, right? And then if this was 9 squares for 0.3 meters, we multiplied, excuse me, we multiplied the distance by 3 to get that 9, right? So in the same way, we're going to multiply 0.4 by 3 in order to draw this diagram to scale. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, perfect. So there is our next point. We're calling point P. Okay. Now, you guys know that when we're finding the electric field strength, we're assuming that the point, in this case P, that is in the electric field has a negligible charge. So the only charges that we need to think about and really calculate, the only charges that we need to factor into our calculations are the charges of Q1 and Q2. All right. So I want you guys to imagine. Let me get a sip of water real fast. I don't have coronavirus, don't worry. I don't think. That's not a joke. I really don't think I have it. So basically, let's think about, first of all, let's draw this distance. Okay, this is 0.4 meters, right? Now, this is the same proportion as this is a similar triangle to a 3, 4, 5 triangle, is one way you could say it, which means that we know that if the two legs of this right triangle, because we know this is your right triangle right here, if the two legs are 0.3 and 0.4, we know that the hypotenuse is 0.5. So let me get a straight edge. I have a ruler right here, so I can draw this hypotenuse. You guys cannot see the ruler, but I am using a ruler. Let me make sure we're still recording. Yep, we're still recording. So now I'm going to draw this hypotenuse. We'll see if I can make it look good. Wow, that was a good hypotenuse right there. So we're going to call this distance of the hypotenuse, the length of the hypotenuse, 0.5 meters. Guys, if some of this explanation feels like kind of confusing, I'd recommend that you, I'll give you a recommendation that doesn't sound that fun, probably. Watch the Class 80 explanation video again, if this is sounding like really confusing, because this is the things I'm saying I'm basing on what I already said in the last video. Now, before I do anything else, I'm gonna label these charges. So Q1 is 7 microcoulombs positive, so that's 7.00 times 10 to the negative 6 coulombs. So that's micros to the 10 times 10 to the negative 6. And then Q2 we know is negative 5 times 10 to the negative 6 coulombs. So I just converted the microcoulombs to coulombs. Easier to deal with that way. And as you guys know, we should be using scientific notation in all the numbers that we calculate, including the angles. And we should be rounding to the hundredths in all our calculations. If we do that, then we should get exactly the correct answer, just for fun. So then we can see our progress and look back on it. I'm going to write the correct answers up here, so then we can eventually see if we can corroborate our answer at the end of the process with the official answer from the book. This is the same answer that you see in the example problem in the book on page 574 and 575. So the answer is 2. Wait, my pen's not working. There we go. 2.71 times 10 to the 5. Remember, the units for electric field strength are newtons per coulomb. Newtons per coulomb, capital C. And then the angle is at 66.6 degrees north of east. Okay, so there's the answer that we should get. It's going to feel really good when we finish this whole process, north of east. And then we can look back at these answers, this magnitude and direction of electric field strength, and it's going to feel so good to get the same answer that we already wrote down here. But that E is bothering me because it looks kind of ugly. North of east. Oh, that looks way better now. So we already have our distance diagram. Before we finish with this diagram, let's get the angles, because those are going to help us. So we can use trigonometry, obviously, to find the angles. I'm going to find the angle at Q2 right here. So that's going to be the inverse tangent of 0.4 divided by 0.3, opposite over adjacent. So, because you know that the tangent of the angle is opposite side over adjacent side, if it's a right triangle. So I'm going to go inverse tangent of 0.4 divided by 0.3. You get 5.31. 5.331 times, I'm going to draw it outside the diagram. So this angle is 5.31 times 10 to the 1 degrees. I'm not going to put the degree sign right there because then it looks like times 10 to the 10. So we're going to say degrees. Now I know it looks weird to write this angle as 5.31 times 10 to the 1, because we know this is the same as saying 53.1, right? But I'm going to leave it in scientific notation just so we can be consistent with all of our calculations doing that. So we know if this is 90 degrees and this is 53.1 degrees, then we can just we can use the triangle sum theorem to find the angle at P. That way we don't have to do more trigonometry. So 90, so we can say 180 minus 90 is 90. 90 minus 53.1 is 36.9, or you can say, like we're using scientific notation, let me go like this. Arrow, I'm going to draw the angle here, write the angle here, 3.69 times 10 to the 1 degrees. Okay, so 36.9 degrees. Sweet. Now those angles are going to help us when we draw the in this case the electric field vector diagram. last topic we were doing a force vector diagram. This time we're doing an electric field strength vector diagram, or electric field vector diagram. All right. So basically I'm going to change to a different color and kind of explain to you how we're going to form this next diagram. So let's go red. Right now I'm at 0.5 millimeters. I'm going to go really thick. There we go. So now, yes. Let me explain to you the situation. So we have two significant charges in this diagram. Yes, there's technically a charge at this point, but like I said before, it's negligible. Okay, before I say this, let me say one more thing. Guys, if there's something there's something that I do here, like the trigonometry or any of the calculations that you don't understand, and you like have really tried to understand it and watch the video, even like slow it down if you need to. If you still don't understand, please email me, because this content that we're learning, you know, I plan to put on, this will probably come on the Partial 4 exam, because we're already in Partial 4 content, even though the Partial 3 exam has not happened. I don't plan to put this topic on the Partial 3 exam, because the Partial 3 exam, the last topic on that exam right now, my plan is to have the superposition principle being the last topic. And eventually we'll talk about the exam review, so don't worry about that right now. So all that said, there's only two charges that we need to calculate it for, and it's these two. Okay, now think about it like this. We want to find the net electric field strength, or we can say the resultant electric field strength at this point. Okay, so in other words, if we have a positive charge here, this electric field is going to be, in a sense, pushing that little tiny charge upwards. And then because this one is negative, like I talked about last class, in a sense, it's going to be pulling that little point charge down and to the right. Okay, so now we're going to draw this situation to scale using electric field strength vectors. Okay, before we can draw that, we need to find out how much is that force, right? I'm going to say force equals how much, and we also need to know how much is this force, right? Wow, there it is. Once we have the two magnitudes of the forces, and actually, sorry, I shouldn't actually say force, because we're talking about electric field strength. So I'm going to say, instead of F, it's going to be E in both these cases, because that's the variable we're going to be calculating for, is E, electric field strength. So now once we have this electric field strength and this electric field strength, then we're going to put them as a ratio. So then we know to what scale we should draw. I shouldn't say to what scale. We'll know how long each electric field strength vector will be in the diagram that we draw next. Okay, so let's calculate these electric field strengths. It's not going to be too bad. Not going to be too difficult. Oh man, now let me do. Oh, actually, I'm gonna go like this. I was trying to erase it all, but it was gonna be easier just to get rid of all this red. Okay, good. Almost ready. Thank you for your patience. Good. I'm gonna leave these two red arrows to help us remember what direction the electric field strengths are acting in. Okay, so let me go back to blue here, and I'm gonna go nice and thin again. All right, good. Let's find, I'm going to go actually really, really skinny, and we're going to zoom in. All right, so let's find the force right here. Let's go to a different color. We'll use black, so we don't get too confused. So the formula I gave you guys last class, the original one I gave you is more complicated, but when you simplify that formula and you realize, as I said last class, that the Q sub zeros cancel. In other words, the charge of this cancels because it's on the top and bottom in the original formula. The formula that we can actually use is electric field strength equals K, so 8.99 times 10 to the 9, times the charge of the charge that is creating the electric field, right? All divided by the distance from that point squared. Okay, so you guys know already what is K, 8.99 times 10 to the 9. So I'm going to say E equals 8.99 times 10 to the 9, like that, times Q, right there, right? 7 times 10 to the negative 6, all divided by the distance squared, so 0.4 squared, right? So when you plug all that into your calculator, let me do that, and then if you want, you can do it too. 8.99. I recommend that you do it. but I can't control you, so do what you want. 8.99 times 7 e negative 6, all divided by 0.4 squared. And you get this e is equals 3.93 times 10 to the 5. Right? This is newtons per coulomb. All right. So that's gonna be our first electric field strength vector in the force vector diagram. All right. So let's do that same thing now, but using this situation over here. So the only thing that changes in the formula is going to be the q in the second case is going to be different, and the distance is different. So now the q that we're going to use is this charge, and the distance that we're going to use is this distance. All right. So E equals 8.99 times 10 to the 9. Yep. Then we're going to say times Q is negative 5 times 10 to the negative 6, negative 5 microcoulombs, all divided by the distance squared, 0.5 squared, right? So let's plug all that in, 8.99 to the calculator times, and remember, I want to say one thing before you plug that into the calculator. This negative, what is this negative actually saying? Right here, what is that saying? It's describing the fact that this electric field is attractive. Okay, so if you use a negative in your formula, it's going to cause problems in the vector diagram because the vector itself is really, it's a distance, it's a magnitude and a direction, right? And if you have the negative in your formula here, it's like you're saying negative twice because we already agreed that this is an attractive force. So what we're going to do is we're going to get rid of that negative because we already agreed that it's attractive, right? And that makes sense to everyone. Very similar to what we did in the superposition topic. Okay, so 8.99 times 10 to the 9th times positive 5 e negative 6 divided by 0.5 squared, right? And you get, now let me tell you what I get. I get 1.798 times 10 to the 5, okay? Now, we're going to round to the nearest hundredth. So the 1.79 becomes 1.80 because after the 9 is an 8. So this electric field strength that you get is 1.80 when we round correctly to the hundredths times 10 to the 5 newtons per coulomb. Sweet. There's our second vector that we needed. Okay. So just like we did in superposition, we're going to take the ratio of this force. Let me change colors again. We're going to go fat. All right. We need to take the ratio of not this force, this electric field strength and this electric field strength to know how long each vector should be. Okay. So let's do this. Like that. And I'm going to, we'll use green. And that's green. Yeah. And we're going to go 3.93 times 10 to the 5 all over 1.80 times 10 to the 5. So let's do that real fast in the calculator. And I get 2.18 is that ratio, okay? 2.18. Now, And this is times 10 to the 0, so just 2.18. Now I'm going to put this over 1. So we're going to say the easiest way for me to do this is to convert this to be equals 1 over something. So cross multiply. Fundamentally, you're going to do 1 divided by 2.18, right? And you get 4.58 times 10 to the negative 1. So that equals 1 over 4.58 times 10 to the negative 1. 4.58 times 10 to the negative 1, right? That's the same as saying, 0.458, because this negative 1 means move the decimal one time to the left, one place to the left. So for me personally, I am going to write, I'm just going to, so that it's easier, we're going to say 0.458, just so that so it's less confusing. So this is, this number is about double this number, right? So that means our first vector, which corresponds to the 1, is going to be about double the length of this vector. So now let's draw these. Remember, the first vector is going to be directly up, and the second vector is going to be down and to the right. And we know this angle right here because we calculated it using trigonometry right there, right? So let's draw this to scale. So if we're going to say the first vector is 1, I'm gonna make that 10 squares. All right, let's say it's 10 squares. So we're going to start right here. We're going to go 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that distance right there, I should say that vector, corresponds to the 1, right? That length. Now, the next one, if we said this is 10 spaces and it corresponds to the 1, how many spaces does that next vector need to be? Well, between 4 and 5 spaces, right? Now, here's where it gets, instead of drawing these using the squares, I'm going to draw it using my ruler because I can't really count spaces diagonally on the screen. So I'm going to make this first vector, we're going to say 10 centimeters. That'll work well. So you guys can't see it, but I'm using my ruler here, and I'm going to draw it as 10 centimeters directly up. So there is my first vector, 10 centimeters. And let me draw the direction right here and draw the points on each end, right? And let me label the electric field strength right now. So this electric field strength corresponds to this vector, right? So we can write 3.93 times 10 to the 5 newtons per coulomb, right? Now let's draw this next vector down in that direction. And if this right here was 10 centimeters, then how many centimeters would be the vector that corresponds to this? Well, it's going to be 4.5, 4.5, 4.6 centimeters. So basically 4.5 centimeters. So here I have my ruler. You guys can't see it again, but I'm using my ruler, and I'm going to draw this next vector. Actually, before I use my my ruler, I'm going to get the protractor so that we can draw the angle correctly. So I use my protractor. Basically, like, you guys can't see it, but let me trace my protractor. I'm using this protractor above the screen, right? You guys know exactly what I'm talking about. And I'm going to measure the correct angle right there before I draw the vector. Okay, and the angle we know is going to be this 3.69 times 10 to the 1, or 36.9 degrees. right? That angle that we already talked about. Guys, what's so cool is that all of this is going to get us the exactly correct answer after all this work. So let me draw this 36.9 degrees. Is that how much I said? I already 3.69 times 1. 36.9 degrees is how long is the angle it needs to be. So using my protractor, I'm going to draw 36. All right, so I just made that angle. So now we're going to draw this vector to be about 4.5 centimeters long. Okay. At that angle, you guys can see that point I made right there. That represents the angle. And 4.5 centimeters. About. And there it is. I just realized something else. The 10 centimeters that I measured, wow. I'm going to leave this angle here, but leave that little dot. But this 10 centimeters I measured is different than what it was before because I've been zooming in and out. Because 10 centimeters at this zooming is different than 10 centimeters at this zooming. So let me get my ruler and make sure I'm at the right scale on my screen. The good thing is you can't zoom in on your paper, so whatever you drew for 10 centimeters is exactly what you had before. All right, using my ruler, now I'm at 10 centimeters. Good. Now I need to not zoom in or out anymore until I draw this. All right, so now, and the reason I know this is because when I first drew that little piece, I was like, that looks way too small. And then I realized that it's because the zooming. So now let's draw these 4.5 centimeters at this angle. There we go. So there's our second vector. We know corresponds to the 1.80 times 10 to the 5. That's the electric field strength. So 1.80 times 10. Let me go. I'm gonna write this really small. Super small. 1.80 times 10 to the 5 newtons per coulomb. Let me write this other one super small too. 3.93 times 10 to the 5, right? Newtons per coulomb. That way I can get rid of this. The reason I'm writing them really small, some of you are thinking this. The reason I wrote these super small is because we're going to have to draw these, we're going to have to make a rectangle. And if these are super big, then it's going to get in the way. But now let me get rid of that point right there. Now we're ready to, first of all, let me draw the direction of this vector. So I'm going to go like that and draw this point here. Now let's make our rectangle so that we can use trig to eventually find the resultant. The resultant electric field strength is that right there. Okay, so let me make it red and we'll draw that. So we need to find, first of all, this red vector, resultant vector I'm going to draw. So let me go. So that vector is up and to the right is the resultant, right? And then the angle that we eventually need to find is north of east, okay? So well, that was weird. That angle, we're going to say theta r is the resultant angle. And I'm going to say E, let me get the skinny, let me make this skinny again. We're going to say E r is the resultant electric field strength given these two different electric fields. And then right here, let me write this smaller. Theta r is the resultant angle, right? So now everything that we're doing from here on out is what you've already done. Very similar to what we did with the superposition principle. So let's draw a rectangle and then see what we can do, what trig we can do to find the E sub r and theta sub r. Let's make the rest of our rectangle blue this time. All right, so first I'm gonna go, I guess we'll draw this part first. Oh, I need to make my lines thicker. All right. And you can see the right triangles forming, which are really nice for SOHCAHTOA. Now, something that we haven't been using, but I've realized we could have been using in some of our problems is the law of sines. I don't know if you guys learned the law of sines in 9th grade, but you don't actually need it because you can still use SOHCAHTOA. If you use the law of sines and you already have some angles, then that can actually take you less time than using SOHCAHTOA. But because I talked about SOHCAHTOA in the last explanation class, we're going to use SOHCAHTOA. So let me draw this angle first. I'm going to make it black. And we're going to make it nice and skinny again. So 36.9 degrees, right? And then the other one was 53 what? 53 point what? 53.1 degrees. So right here, if this is 36.9, we know that the other part of this 90 degrees is 53.1. 53.1 degrees, right? Now, if this right here is 53.1, we know that this right here is also 36.9. 30, let me go even skinnier. Oh, whoops. 36.9 degrees. Cool. All right, sweet. Now we're getting close. Now this is actually easier than the rectangle that we were using in the superposition principle because look, this entire side right there is the same length as this entire side. So let's just draw that. Let's just write that length right away. So we know that they're both, and it's not really a length because we're talking about electric field strength, but these are vectors that we can kind of treat like lengths in a problem like this. So we're going to go, let's go blue again. So again, 3.93 times 10 to the 5 newtons per coulomb, right? So now let's think about, we eventually want to find this, the length of that vector and this angle. So I'm thinking, okay, we need to find the length of this little guy and this little guy. And then we can use Pythagorean theorem, and then we'll be really close to finished. So what I'm going to do is I'm going to find the length of this guy. Let me move something real fast. Go like that. Move this. Make it a little bit smaller. And then I'm going to say, I'm going to go all of that. Wait. You know that all of that is 3.93 times 10 to the 5, right? So now let's find, I'm going to go black, and we want to find just that piece, right? So just that piece, we can, you know that we have the hypotenuse right there, and we have the angle. We can use this angle. So let's find, and that means that this side right here, we need to find is the adjacent. So adjacent to hypotenuse, cosine. So I'm going to say cosine of 36.9 equals the adjacent, what we're trying to find, right, over the hypotenuse. So fundamentally, we're going to do cosine of 36.9 divided by all that, divided by 1.80 times 10 to the 5, right? So you get, wait a second, cosine 36. Let me check my original. Yeah, let me do this again. Cosine of, I just realized something. 1.8 times 10 to the 5. 1.8 times 10 to the 5. No, we're good. I thought I copied one of my values incorrectly and that it was going to screw up our entire problem, but I think we're good. So using cosine, let me draw this a little bit nicer. I'm going to change this to red. Thank you guys for your patience, all this stuff. Okay, so we're going to find that red length, in a sense, quote unquote length. So cosine 36.9, and then times 1.8 times 10 to the 5. Here we go. You get 1.44. 1.44 times 10. And remember, I rounded 1.439 to 1.44 times 10 to the 5. There we go. Newtons per coulomb. Okay. Now, what you're thinking right now, many of you, is, we can now find this length because, this length right here is this minus the 1.44 times 10 to the 5, right? So we're going to go 3.93 times 10 to the 5 minus 1.44 times 10 to the 5, and you get 2.49. Yes. Let me draw a little red thing here. This length, we get 1.49. Sorry, not the 2.49 times 10 to the 5, right? Newtons per coulomb. Now look, we have this leg of the triangle of our resultant, but we still need this little piece right here, and we can find that by finding this over here, right? So I'm going to use the hypotenuse we know is 1.8 times 10 to the 5, and I'm going to use the 53 to find this side, right? So so we have the hypotenuse, and this side is the adjacent to 53.1. So adjacent to hypotenuse, once again, cosine. Okay, so we're going to say cosine 53 equals the adjacent, we don't know, over hypotenuse. So really, cosine 53 times 1.8 times 10 to the 5. Cosine 53.1, sorry, I said 53, but cosine 53.1 is a number, right? Some number, and then times 1.8 times 10 to the 5, and you get, yes, 1.08 right here. This length is 1.08 times 10 to the 5 newtons per coulomb, right? So if that is 1.08 times 10 to the 5, then this down here is also the same, 1.08 times 10 to the 5 newtons per coulomb. Sweet, we are so close. Newtons per coulomb. Sweet. All right, guys, Pythagorean theorem will give you, using this as A and this as B, A squared plus B squared equals C squared, or you can use, as we've talked about many times, this can be A and this can be B. We'll give you, using Pythagorean theorem, we'll give you C. So I'm not going to write up the Pythagorean theorem, but you guys know it. So do the Pythagorean theorem, and you will get a value for E. If you want to pause it, you can try that yourself. I'm going to do it right here, and then we'll see if you guys get the same thing as me. 1.08. Don't forget that in the Pythagorean theorem, both these numbers are squared. And then and then you need to, you know what, let me just write this. I'm gonna go black. Come on. A squared plus B squared equals C squared, right? So fundamentally, to find C, square root, you want to find C. So if you square root C squared, then you get C. So your answer is going to be the square root of that squared plus that squared, right? That's what will give you the value of C. So do that, and I'll do it here. My calculator. I'm not going to write out all of that because it's just a lot that you guys know how to do. Almost done. I need to make sure I didn't make a mistake. Fine. Square good. Square root. Wait a second. Square root of that, and you get yes, let's go. I love it when we are correct. It feels so good. I'm going to draw this. Now we're going to use a special color to express our answer. We'll use a color we haven't used before. Right there. So guys, when you do all that, you get exactly the answer that you needed, that we found, that we said the answer would be 2.71 times 10 to the 5 newtons per coulomb is the magnitude of the resultant electric field strength, you guys. Right there. There's the magnitude of the resultant electric field strength. Now, before we go and look at our answer and celebrate that we got the correct answer, let's find the angle really fast. So to find this angle right here, I'm just going to use tangent. We have opposite, adjacent. So use SOHCAHTOA, use tangent to find that angle. So really, fundamentally, we're going to do the inverse tangent of this opposite divided by adjacent. So let's do that real fast. Eight E5, and you get wow, you guys, life is good. Wow. Now, like I told you guys, we're going to round to the nearest hundredths using scientific notation in our calculations. So when I get this answer in scientific notation, I get the angle is 6.655. Well, yeah, 6.65, but there's a 5 after it, right? So really it's going to be 6.66 when we round that correctly, times 10 to the 1, which equals 66. Oh, do you feel the power? 66.6 degrees. And we know that we started east and went north, so it's north of east, right? North of, I'm going to say north of east, right? So there, let me go like this. There's our angle. So let me write both of these together, just so that we can feel the satisfaction of having done all of that. I'm going to get rid of this Pythagorean theorem junk because we don't need that. It looks messy. The rest of this looks pretty good, pretty clean. So we're going to say let me make this pen thicker. The resultant electric field strength is 2.71 times 10 to the 5 newtons per coulomb, right? At what angle? 66.6 degrees north of east. All right, so there's our answer. Boom. Now let's compare that with the answer we said that we would get. Yeah, okay, so wow, we did so much calculations. Look at that. There is the answer. They said and I told you 2.71 times 10 to the 5 newtons per coulomb at 66.6 degrees north of east. And look, exact same answer that we got. You guys, incredible. Let's do this. And then you're free. I'm gonna select this, copy it, right? Now I'm gonna paste it over here, paste, shrink it down a little bit. Oh, look, it copied this little guy too. Wait, copy that too. And look, you guys, there is our answer, exactly the same as what we should have gotten. So thank you guys for your attention. Let me just draw this arrow so we can celebrate. That's our celebration arrow. Let's see how long that took us. That one problem took us 45 minutes. 45 minutes. You guys should be proud. Let's get all of these calculations all in one page. Oh my goodness. You guys, we did it. That is everything. As you saw on the worksheet instructions, don't forget that you have to send me your whole process and correct answer before 11:59 on the day this solution video is released, which would be today if you're listening to it on the day it was released. And that is everything. Good job if you understood that. If not, watch the video again, and we will see you guys next class. Peace out.